All right, today we're diving into a pretty radical new vision for artificial intelligence. What if, instead of programming intelligence line by painful line, we could just grow it? Let's unpack this idea of building intelligent systems from the bottom up. So it all kicks off with this simple but really deep puzzle. How is it that an AI can absolutely crush the world's greatest chess masters, a game of pure abstract logic, and yet we can't build a robot that can reliably walk into your bedroom and just make the bed? I mean, one is this pinnacle of strategic thought, the other is just folding sheets? So what gives? Well, the answer reveals a massive, fundamental crack in the foundation of traditional AI. And to really get a handle on the solution, we've got to first understand the problem. And that problem is all about the classical top-down way of building AI, an approach that a lot of people now see as, well, basically a dead end. The classic metaphor here is perfect. Think of old-school AI as a brain in a jar. It's this pure, disembodied mind that just shuffles abstract symbols around based on a set of logical rules we give it. It knows the symbol for king can move one space, the symbol for pawn can move two. But here's the kicker. The AI has zero idea what a king or a pawn actually is. They're just tokens in a game, totally meaningless outside their little logical box. And that right there leads to the first huge roadblock, the grounding problem. If your entire universe is just symbols, how do those symbols ever connect to anything in the real world? The symbol for chair inside the computer is just a label. It's not connected to the experience of sitting, the feeling of wood, the sight of four legs on a floor. Without that connection, the symbols are ultimately empty. Then you hit the second massive hurdle, and this one's a doozy, the frame problem. Okay, imagine a robot picks up an apple. Simple, right? Its programming has to update its internal map of the world. The apple is now in my hand, not on the table. Check. But what about literally everything else in the universe? It also has to know the table is still there. The walls haven't changed color. The sun is still in the sky. The list of things that didn't change is basically infinite. Trying to track all of that after every single tiny action is a computational nightmare. It just explodes. And this quote just nails the grounding problem. You can tell a robot to go to the recharging station, but without any real-world grounded understanding, what do those words even mean? Is it the shape, the plug, the flow of electricity? Without any physical experience to connect that label to, the robot is just completely lost. So, if the top-down, brain-in-a-jar approach keeps hitting these fundamental walls, what's the alternative? Well, you have to flip the entire model on its head. Instead of trying to program intelligence from the top down, you grow it from the bottom up. You know, the old way is kind of like trying to build a person by starting with a PhD in philosophy and then trying to teach you how to walk. It's completely backward. The new bottom-up approach says, nope, let's start with the basics. You start with a physical body, with senses, with bumping into things, and you let complex behaviors and eventually intelligence just emerge from all those simple interactions. And this leads us to the core thesis of this new way of thinking. Real, adaptable intelligence isn't programmed with abstract logic. It emerges from the messy, direct, physical experience an agent has with its environment. In this view, to be truly intelligent, you first need a body. Okay, so that sounds cool in theory, but how in the world do you actually build something that way? You can't just write a program for emergent intelligence, right? You need a totally different set of tools, a toolbox that's inspired not by computer science, but by biology itself. Tool number one in our new kit is the brain, or at least our artificial version of it, artificial neural networks. Now, instead of one big central processor executing instructions one by one, an ANN is made of tons of simple little units all connected together, all working in parallel. Just like the neurons in your brain, their collective activity is what creates complex behavior, and there's no central boss telling every single one what to do. Next up, tool number two is the blueprint, and this one is straight out of Darwin's playbook, genetic algorithms. It's a search method that basically mimics evolution. You create a population of potential solutions, code it up like genotypes, you test how well they do a task, that's their fitness, and the best ones get to reproduce and create the next generation. Throw in some random mutations, let it run for a while, and you'll see amazing solutions evolve all by themselves. And that brings us to the third, and maybe the most mind-bending tool, the growth process, or artificial embryology. With this, the genetic code isn't a direct blueprint where gene A builds part A. No, instead, it's a recipe for development. It's a set of rules that guides a process of growth, starting from a single cell, that results in a complex final form, a phenotype. The best analogy is the difference between a Lego instruction manual and the recipe for a cake. The recipe doesn't describe the final cake, it describes the process that creates it. So, what happens when you combine these three amazing tools? You get a system that has a neural network for a brain, a genetic algorithm to evolve it, and a developmental process for growing it. And the result is something truly extraordinary, a system that can grow, learn, and evolve all on its own. This whole process looks a lot like biology. You start with a single cell, a zygote. The developmental recipe in its genes guides how it divides. Critically, cells only communicate with their immediate neighbors. There's no master plan from on high. But from all those simple, local interactions, a complex global pattern just emerges. It's all about bottom-up self-organization. And if you want to understand the sheer power of this, just think about us. A human body has around 50 trillion cells, but our DNA, our developmental recipe, only contains about 30,000 genes. That is not a one-to-one blueprint. It's an unbelievably compressed set of instructions for a self-organizing process. Nature uses this trick because it is insanely efficient. And this efficiency is a complete game changer for evolving AI. Check out this chart. It shows how big the genetic search space is to create a simple 128 by 128 pixel image. If you do it with direct encoding, where every single pixel needs its own gene, you need over 16,000 genes. That's a massive space for evolution to search through. But with a developmental system, an AES, you only need 144. The search space is exponentially smaller, which makes it vastly easier for evolution to find good solutions. Now let's add another layer to this, learning. There's this incredible phenomenon called the Baldwin effect, which shows how learning can actually guide evolution. So imagine an animal learns a new useful behavior that helps it survive and have more offspring. Well, over many generations, evolution might start to favor any random genetic mutations that make learning that behavior a little bit easier, until eventually what started as something you had to learn becomes a hardwired instinct. Learning literally smooths the path for evolution. But individuals don't have to learn everything from scratch, right? That's where cultural evolution comes in, adding a new, even faster layer. Instead of waiting for genes to pass down vertically from parent to child, agents can share memes, these little units of cultural information, horizontally with each other. This lets good ideas spread through a population like a virus, speeding up adaptation for the entire group without slow, painful trial and error. So you can see the parallels. Both systems have these units of information, genes and memes, that replicate and are subject to selection. But the way they work is really different. Genes are slow, passed from parent to offspring over generations. Culture can be passed between any two people at any time, and its spread is filtered by conscious choice, not just by raw survival. So let's zoom out. What does all this mean for the future of intelligence? Where does this bottom-up, bio-inspired approach actually lead us? The key takeaway is this. When we build AI using nature's strategies, we end up creating things that share nature's best properties. They're more scalable because of those compressed genetic recipes. They're way more robust because the developmental process can handle unexpected damage. In fact, get this, experiments have shown that some of these evolved systems can actually regrow parts that get damaged, a property that nobody ever explicitly programmed into them. This quote from the source material really captures the massive paradigm shift here. We are no longer designing the final product, we are designing the process of design itself. We're building evolutionary systems that can then go on to discover and invent solutions all on their own. We're moving from being manufacturers to becoming, well, creators of creators. And all this leaves us with a final, pretty profound question to think about. If we create intelligence through a process of evolution and development that we guide but don't fully control, what is our relationship to it? Are we still its programmers in the traditional sense? Or are we just setting the initial conditions, kickstarting an evolutionary lineage, and becoming, in essence, the ancestors of a new form of artificial life? It's a lot to chew on.